Okay, so today we are going to take a look at normal distributions. So far, we've just taken a look at probability distributions for discrete random variables, but for continuous random variables, x can take on a fractional or decimal values. So the graph of a continuous probability distribution is going to be modeled with a smooth, continuous curve. Probabilities can be computed by finding the area under the curve. A little bit of calculus there. If you're going to go study further on into calculus and statistics, you will be able to do that from first principles, but not in this course. Okay, I used to do this as an introduction in class, but I'm not going to get you to do that right now. This is what the continuous distribution of a normal look like. Look familiar? A normal distribution, a random variable that is normally distributed, looks like the mound shape. Back when we did our histograms, except this is for continuous data, so your boxes are so tiny that it's imperceptible, and so it becomes this nice smooth curve with a mound in the middle. And in the middle is, if you remember, your mu. Remember, mu is the mean for the population. And then moving away from your mu, if you go up, remember what this is? 1 standard deviation. So if you calculate what your standard deviation is, and from your mean, you go up 1 standard deviation to get to this limit. And if you go back to your mean and go down 1 standard deviation, in other words, you subtract a standard deviation, you get this limit. And so this area underneath this curve would represent 68% of the entire population. Okay, so a good chunk of it, right? A little past 2/3. And now if you continue, but instead of going up just 1 standard deviation, if you go up another standard deviation, or if you go up 2 standard deviations to this limit right here, which we call your mean plus standard deviations, go back to your mean and then subtract not 1, but 2 standard deviations. You're down here. So the area underneath all of this curve, I'll color that in red, all this red section there is obviously going to be more than 68%, and it is actually 95%. So we say within 2 standard deviations of your mean, you have 95% of your population. And then if you continue with the same pattern, but go up 1, 2, 3 standard deviations, looks like it's almost the entire curve, but not quite, because remember, this is a continuous curve. It will go on and on forever and ever to positive and negative infinity. But if you stop it at 3 standard deviations away from your mean, that is 99.7% of your population. And these numbers are so important. They're referred back to again and again in studies, statistics, all kinds of work, and we call that your empirical rule. Oh yes, and just a reminder, X bar is for the mean of a sample. But right now we're talking about mu, so that is a population. So within 1 standard deviation of your mean, you have 68% of your population if it follows a normal distribution, and it is a continuous random variable. Within 2 standard deviations from your mean, you would have 95% of your population, and within 3 standard deviations from your mean, you would have 99.7% of your population. So there's some properties that I want to point out about normal. It is symmetrical about your mean. So your mean, median, and mode are equal, and they follow the line of symmetry for this curve. It's shaped like a bell, peaking in the middle and sloping down towards the sides, and approaches 0 at your extremes, your right tail and your left tail. Approximately 68% of the data is within 1 standard deviation of the mean, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. That's what we just covered. But here's a little bit about notation. Notation for normal would have a variable of, say, x. So we would say x, and then this tilde here is labeled for distributed. So x is distributed like a normal with a mean of mu and a variance of sigma squared. And sigma would be your standard deviation. So remember, sigma squared is your variance. Okay, if you want your standard deviation, what number is there would be your standard deviation. So quite often we do it like this. We say x is distributed normally with a mean of 10, a standard deviation of 4, and we put 4 squared in the backspace here for your variance. All right, so let's try an example here. We've got Laura, who's an engineer, designs roller coasters, and she wants to develop a ride that 95% of the population can ride. The average adult in North America has a mass of 71.8 kilos with a standard deviation of 13.6. What range of masses should she be prepared to anticipate? Oh, let's just cover up the second part there. Well, if we assume the data is represented normally, then two standard deviations would cover 95% of the population. Our standard deviation was 13.6, and we want to be two standard deviations away from our mean for 95% of our population. So you double 13.6 and go up from your mean to get your upper limit, subtract from your mean to get your lower limit. So you should end up with a range of 44.6 kilos to 99 kilos. Sorry. If she wanted to provide for 99.7% of the general population, what range of masses should she be prepared to anticipate? So 99.7, that refers to 3 standard deviations from our mean. So you're going to repeat this process, but instead of doubling your standard deviation there, you're going to triple it and then add and subtract from your mean. We're going to start at 71.8, add triple of 13.6 to get our upper limit of 112.6. And then we're going to triple 13.86, subtract that from 71.8, and you end up with 31. So the range for 99.7% of the population would be 31 kilos to 112.6 kilos. And then she can design her roller coaster where it wouldn't meet everybody, because obviously you do not want tiny babies with small weights to go on the roller coaster. They would be banged around a lot. And same for very large adults. They would not be able to accompany them on the ride. Okay, so reminder, the area under every normal curve, if you total all of it, the area would equal 1. In any normal distribution, the percent of the data that lies between two specific values is the area under the normal curve, and we usually represent that as a percentage. Okay, so example 2. Let's take a look here. We have a random variable x distributed normally, a mean of 50, standard deviation of 5. Draw a diagram that represents a percentage data that have these values. You want x to be greater than 55. What percent of the population has values greater than 55? Well, it's always best to draw yourself a diagram so you can see what's going on. Draw yourself a normal curve. In the middle is our mean. That is going to be our 50. Because we have a mean of 50 here, and now we're going up by standard deviations of 5. So if we go up 5, we're at 55, and that is the cutoff that we want. We want x to be greater than 55. So we want this area up here, and now we have to figure out what percent lies in this area up here above 55. Well, if we cut it in half, it's symmetric, so 50% would lie all the way from negative infinity up to here. So that's 50%. And this is one standard deviation away, so we would have half of our 68 lie on this side, because the other half is already in with the 50, right? So within one standard deviation, we have 68, so half of it would be 34. So 50 and 34, we would have 84 over here. Take that away from 100%, and we have what's remaining, which is 16%. So the probability that x is greater than 55 is 16%. All right, let's try another example. What if we want between 40 and 60? Well, 40 and 60, well, if you go up one standard deviation, we're at 55. Two standard deviations, we're at 60. Other way, we start here at 50 in the middle. So 1 here would be 45, 2 here is 40. So this is really 2 standard deviations when you're going between 40 and 60. And 2 standard deviations have 95% of the data there. So the probability that x is between 40 and 60 is exactly 95%. And that just comes from knowing your empirical rule. What about the probability that x is greater than 38? Well, 38 doesn't quite fall on one of our exact standard deviations. 40 would be our exact standard deviation. So we're going to leave that for the time being. We'll come back to that in another lesson. Example 3, let's take a look here. We've got 10 marks if two students are going to be compared. Amanda has 10 marks, Sebastian has 10 marks. Calculate the mean and standard deviation for each student. So a little bit of review. The mean there for Amanda is 68.3. Her standard deviation is 8.3. You can use Desmos to calculate those. So just recall, make sure you can do your enter it into your table, and then you use your standard deviation and mean in Desmos. For Sebastian, the mean was 70.5, and his standard deviation is 14.9. So if you compare the two, Amanda has a lower standard deviation than Sebastian, which means she's more consistent, right? So let's see, though, what percent of each student's marks fall within one standard deviation of the mean, assuming their data is normally distributed. So Amanda's mean was 68.3, and her standard deviation was 8.3, so you want to add and subtract, so you get your new limits there. So her percent of marks goes from 60 to 76.6, and Sebastian's marks within one standard deviation, his range from 55.6 to 85.4. And there right away, you can see that Amanda is more consistent for 68% of her results. Now, if you compare to your actual data what falls within 60 to 76.6 for Amanda, you can see in red, I have highlighted here which ones fall in that range. And then for Sebastian, between 55.6 and 85.4, we have these ones. So for Amanda, she had 5 out of her 10. So 50% of her marks fall within one standard deviation of her mean. And same for Sebastian, he also had 5. But what were we supposed to have for one standard deviation? If it was normally distributed, it should be about 68%. So Amanda and Sebastian aren't necessarily normally distributed. Well, let's try example number 4. The mass of 17-year-olds in a data management course is normally distributed. The mean is 65 with a standard deviation of 5. Sketch the curve, including the mean and standard deviation intervals. Now you can sketch your curve. Determine the probability that a student in class has a mass between 60 and 65. So if you switch it to your notation, we want the probability that x is between 60 and 65. There you go, x is in the middle. And that would only be half of one standard deviation. So one standard deviation between the lower and the upper limit should be 68. We only want one side or half of it, so that would be 34%. Determine the probability the student in class has a mass greater than 75 kilos. What is the probability? Well, 65 should be your mean in the middle. So we are going up 2 standard deviations, and we want the upper limit here. We will only want the upper limit. If you had both of them, that would be 5% because 2 standard deviations within it is 95. The left on the tails is 5%. We only want one tail. It's symmetric. So we just cut our 5% in half. So 2.5%. The probability that a student in the class has a mass greater than 75 if they follow a normal distribution would be 2.5%. Okay, and you've got a list of homework questions there that you can practice now with a continuous random variable in a normal distribution. If you have any questions, send them my way.